good to be back here. My name is Raj Kurup. Today I'm talking about self-regulating suspended biogas collector technology. I'm delighted to present this afternoon about this technology, which enabled us to win the Research Innovation Award. As Peter said, last year we got a research award on Research Innovation Award on NMOX technology. So for the past maybe 15-20 years, I have been working in the process engineering side. This project gave me an opportunity to go back to fundamental civil engineering, civil mech engineering area, where I started actually designing floating and fixed cover anaerobic digesters, anaerobic cow materials, and anaerobic reactors. Now, before I go further, I just would like to mention about what we are. We are a specialist engineering company providing innovative solutions for complex problems. And though we are a consultant, we make use of every opportunity to develop new technologies. Probably not a good thing for a place like Western Australia, where there's limited opportunity for innovative solutions, but nevertheless, we continue to do that. So SSBC is one of the technologies we developed. We can also see, NMOX technology that we received the award. We also have a model for NIMP, Nutrient Irrigation and Management model, which is an innovative process, and also phosphorus removal product for catchment areas, etc. And there's another interesting project we developed over the last 3-4 years, and it's going to be employed in a large alumina sector. Is the smart priming oxalate removal enabler called SPOT technology. So we probably might, if you're fortunate, we will be here next year this time, if we can implement that by this time. Also high rate anaerobic reactor technology called HART. Now, probably all of you might know an anaerobic reactor, anaerobic lagoon, pond, whatever. So why we are going for this this technology? This is not a reactor technology, it's actually a covering mechanism to catch a gas. And quite often, you can see that you have a number of anaerobic reactors. It may be completely covered, a monolithic structure, and if something goes inside, you don't have any access. Especially if you have a mixing mechanism, and there is a physical damage to that structure, you want to replace the mixers, you probably don't read that because it may not go along with what I talk. It's a lot more stuff there, and I'm probably talking a little bit more summarized thing. So something goes in there, you can have access. That's problem number one. And if there is any local damage to one point, all the gas will be going out. And if you have a power generation, up to 10 megawatt, whatever, you can't actually then get any trace element, any trace of gas. So your power generation will be completely cut down. So there's a lot of risk involved in this current conventional systems. And we also have extreme weather events, and we know that more and more we happen to see that. And weather events with a monolithic structure like that, I will show some photographs. Even for this one, this extreme weather events, it can cause a lot of damages. This is a fixed cover, and this damage can cause a hole or tear off that, and the whole downstream power generation system will have to be switched off. And now, if you have an existing system which doesn't have an anaerobic system, which doesn't have a cover, and for water, I think a few years ago, Water Corporation had they were addressing an issue with Wiluna. Probably Peter might know Wiluna. I think the Governor General of that time, his native area is Wiluna. I think they have a plant, and it was anaerobic pond, and it was producing a lot of odorous gases. And if you want to retrofit, it's quite expensive, and many contractors wouldn't take the risk. They say, okay, I can do it, but you take the risk. And there are a number of technologies. The earlier one was a fixed cover one. This is a floating cover system. And these are the existing technologies out there. So this is a geodesic dome type thing. And this is also a fabric type thing too. And you can see that the modern which these days, this technology is taking over most of the anaerobic anaerobic reactors, gas capturing system. And you can see here they got double membranes. So the bottom one is, inside the bottom is basically collect all the biogas. This is the biogas collection system. And in between that B area, I think it's the, in between the outside and inside one is where actually they have a pump here. It pumps air into that, so it's always under compression. It's basically you get a constant pressure. It protects it from the biogas cover from having any damage, etc., to a certain extent. But again, it's not cheap, and ongoing cost of maintenance of that is quite high. And again, you wouldn't have any access to inside if you really want to. Dislodging is a problem if something got stuck. If the system of dislodging doesn't work, then it's a headache, and you need to basically undo everything. And then you fix it as if it's a new system. So why did we go for developing this system? We had a client a few years back, and we installed a reactor. The contractor was good enough. We were just a consultant. The contractor said, well, we can cover it later, a couple of years later. Let's go and do the reactor first. Then the Prime Minister at that time would give more money. Carbon CPRS, etc. was at that time. So the client said, fine, let's wait for that. And after 2 years, we wanted to cover it. The contractor, never there. He disappeared. And we called other people, all the other companies who would do the covering systems. They said 2 million. So the client said, no way. So we thought it's a challenge. Let's work on a new system. So we were looking for an easily retrofittable system to existing gas covering system to existing systems, and also probably a bit more of the time of the day, IoT. Let's have a remote automatic control systems, online monitoring. If there is a storm event coming, we know it's coming. Bureau of Meteorology's data would be available, so the system can automatically work in a level that it gives less damage to the system, to the gas holding system. And it can also be easily repairable without shutting down the power generation downstream. So that's the most important thing, especially if you have a power generation, you need reliability. And every time you want to repair your system, you don't want to shut down your power generation. Because it's modular, if one of the covers got damaged, you can still the remaining ones will function, so you still get power supply there. And other issues like rainwater management, water level fluctuation, all the other issues with that you currently face with the existing technologies, we can easily overcome. So this is a reactor which under construction time. And it's quite large, 32-meter diameter, so you can assume that it's a very big reactor, and 6-meter tall. And we looked at a number of options, and we came down to 2 options. It looks very simple, and believe me, a lot of structural, mechanical, hydrostatic, all sorts of calculations we have done to finalize the design. So we had a series of rectangular tanks where they would flow, but any wind event or any event, it can actually stabilize by itself, and it wouldn't topple. And then I know 2 humans don't like each other, so also 2 gas holders may not like each other, so try to collide with one another. How do you take the energy that provided, that released when they bombard each other? That's a shock absorbing system there. So this is one of the systems we trialed. The other one is a linear one from end to end, like a stripe. So we did all the calculations, and you can see here, this is the area where we also have a regulatory system here. Not regulatory like your regulatory, but it's a regulation system where you can actually control the weight, the pressure inside, and also if there is a windy, extreme storm event happening, we can actually control how much it can go down so that the wind will pass through that, doesn't get toppled, or it doesn't affect the system. And the buoyant material, doesn't have to be connected to the base or to the side. So you just put like this cup, you can put it there upside down rather, but it doesn't have to be connected to anything. So if you want to take out, you can easily take that out. like you have a number of gas holders, and if one is damaged, you can just take that out without affecting the entire process. So this we have done a number of calculations and modeling, and we found, and then we also which material you need to use. We found stainless steel, galvanized iron, fiberglass, high density polyethylene structures, and also ferrocement. I don't know anyone knows the word ferrocement. Apparently, it's back to my university days, undergrad days, where ferrocement is a way of constructing thin concrete slabs type thing, using wire mesh, chicken mesh, etc. So it's very easily manufacturable. Now, when fiberglass and other plastic materials came, actually it's no more famous as it used to be in the 90s and 80s. But we tried that as we did the modeling of that one also, how much should be the thickness and how much should be the internal pressure. So all sorts of things we found. We did work on that. Then we worked on the gas pressure inside and the roof dimensions, which is the optimum one for different materials. How much should be that in the central axis, how much it should go below the water level, etc. So we actually, I'm just giving you all the diagrams so that it's not some simple thing that we took the award just easily. No, we had really show you something that we did work very well in order to make it happen. So one of the fundamental things is obviously the cost. Second thing is ease of fabrication and the transportation, craneage, and how you can implement the instrumentation and control system. So as I said earlier, we selected the model number 2. We used the fiberglass with the steel reinforced channels. We used a 3-meter wide gas holder. And then stability and pressure induced by water tank in the center vent, as we call it a water tank. And it can be remotely regulated. And shock absorbers were installed. So we found that it got a number of benefits. Number one is the cost. I don't want to say the actual cost which I can implement for water co-op or whatever, because it gives us takes away our profit from, but is substantially lower than what actually the commercial guys promise for the conventional technologies. And again, if you have is it ending here? Can you go it further from here? Yes. Someone was talking about the evaporation is higher in dams in sometimes. So can we have something in your dam area? Yeah, we can. It doesn't have to capture biogas, but it can prevent evaporation because it's still modular, easily replaceable, take it away if you don't want it. If you have an odorous gas generation situation like Viluna, or if a mining tail dam, you can actually place that in. So capturing odorous gases, not just anaerobic reactors. This is one of my former students who was doing internship with us. So we developed a prototype first, and then so we were trialing this and see how it would work. I had to cut down the video to make the presentation strictly under 5 megabytes. So I had a few minutes of where it's placed. So it's basically, in conclusion, this is a technology suitable for capturing biogas from anaerobic reactors and lagoons, and it can also be used for controlling emission of odorous gases, and also for evaporation for water storage dams. The advantage of this is it can be retrofitted to existing reactors and lagoons relatively easily. The cost is much lower. It's very resilient to withstand extreme weather events. Any local damages can be easily repaired, and without shutting down your power generation downstream. So you just localize one of the gas holders, take it out. Rest of the ones will work. You still get power supply. You don't have to run it in a mode where. Thank you all. If you have any questions, please feel free to ask me. I'll be here. My contact details are here. Thank you, everyone.